Hello, this is the first live session of the MOOC on parallel algorithms. Is anybody online? Lectures of the course are up now. There are about 10 more to go. Mostly in the first half of the course, we have seen PRAM, the PRAM model and algorithms designed on the PRAM model. We saw several algorithm design techniques. I hope you learners would have been listening to the lectures and solving the assignments. So is there anybody with a question? So in this course, we began with an overview of the basic computation models. In particular, we looked at the PRAM model and its variants. There are variants of the PRAM model based on how you handle concurrent reads and concurrent writes. There is the concurrent read, concurrent write model, which allows both concurrent reads and concurrent writes. There is the exclusive read, exclusive write model where neither is allowed. And then there is the hybrid concurrent read exclusive write model, in which writes are exclusive but concurrent reads are allowed. Then based on the conflict resolution schemes that we use for the write conflicts, we have various kinds of CRCW models. So we saw a variety of them and tried to simulate them on each other, found a hierarchy of those models based on the computational power. Then we considered the notion of self-simulation, where PRAM can simulate a larger PRAM of the same kind. And we found that most of our models were self-simulating except for one model. After that, we discussed several basic algorithm design techniques, like the balanced binary search algorithms, the balanced binary tree algorithms, using which we designed a prefix sums algorithm, and then several other design techniques we saw. For example, the accelerated crowding, where you have a certain processor advantage to begin with, and then using this processor advantage, you reduce the problem size. And since you have all the original processors with you, when the problem size goes down, the processor advantage increases. So as this goes on, you have larger and larger processor advantages. So the later instances can be solved faster and faster. And so you have an accelerated crowding, that the processors crowd onto a smaller and smaller instances, and the problem will get solved very fast. We saw such algorithms. Then, of course, we had an algorithm for symmetry breaking, where a linked list was three-colored. On a linked list, when you want to color the linked list with three colors, every vertex looks at the neighbor, and using the present color of itself and the neighbor quickly finds a new color. A new color can be found in order one time, and the new color will be logarithmic in the size of the previous color. So when we keep on doing this, the number of colors used for coloring the linked list will reduce very rapidly. So after some time, we will be left with a constant number of colors, which can further be reduced to 3 very quickly. Therefore, the resultant algorithm runs in order of log star and time, used for 3 coloring a linked list. This can be used as a subroutine in several algorithms, for example, graph coloring algorithms, to break symmetries very quickly. Symmetry breaking is very crucial in many algorithms. For example, finding a maximal independent set is crucial. That is because in many applications, an independence where you model the application using a graph, an independent set is a set of vertices, no two of which are adjacent. So you could assume that these are vertices that do not conflict with each other and can be scheduled at the same time. So finding a maximal independent set can be done using the symmetry breaking algorithm. So it has many such applications. Then we saw Cole's merge sort, which sorts n items in order of log n time on a CR-EWP RAM. We did not see the ER-EWP RAM version of it. We saw the CR-EWP RAM version of it. And then we studied some sorting algorithms on comparator networks, which are, of course, very old algorithms, but have a very low, small constant factor hidden by the order notation. Then we saw interconnection networks, such as linear array measures. So right now, in the 27th lecture, we are discussing some interconnection network algorithms. There are some more to go. In the remaining lectures, we will see some more interconnection network algorithms, and finally, we will conclude the course with some lectures on the complexity class NC, the NICS class, which characterizes the set of problems that can be efficiently parallelized. We shall show some problems that are P-complete for MC reductions in the sense, and in that sense, those problems are rather hard to parallelize. So that will be how we conclude the course. Hope all of you will stay together till the end of the course and find it enriching. Okay, so we are closing this live session. If you have queries, you can keep posting them on the forum. The TS are always checking the questions. They'll be answering the questions. If there are harder questions, then I'll chip in with an answer, as we have been doing. So hope to see you there. Thank you. Hello, Bapesh. Do you have a query? That's okay. Yes, please ask your question. Hello, Bapesh. Are you there? For big data computation, these actually might not be directly useful for computations on any of the existing platforms. But then, as time progresses, the computing requirement of mankind keeps increasing, and the machines are not getting any faster. So sooner or later, we will have to go for massive parallel computation. And then when you think of parallel computation, you naturally have to ask all these questions. How exactly will you uh, parallelize your algorithms? And any parallelization which is automated doesn't seem to produce very efficient algorithms, because designing algorithms is a bit of an art. Human mind is certainly necessary. Therefore, we have to look at all these algorithms. How exactly they will be used, the future will tell. Because the shared memory architectures, half of the course that we have seen were on shared memory algorithms. And shared memory architecture certainly has a limitation, in the sense that the fan-in, fan-out constraints make it difficult to design machines with very large parallelism. Hopefully, we will overcome this someday, but as of now, it is not possible to design massively parallel shared memory machines. So the machines that we are going to have will be with a small number of processors. But when you have only a small number of processors, how exactly are these algorithms going to be used? I think we had discussed this in some of the first few lectures. These algorithms are all designed on self-simulating models. So you can, after all, simulate those algorithms on the smaller machine that we have. But there is also the philosophical issue. I mean, once you are presented with a problem, you have to also ask, how far is this parallelizable? We are trying to answer such questions here. Yeah, do you have a comeback? There's a message here. I cannot read it. Yeah, so that's what I said. The multi-core machines that we have, in fact, have very few processors. Okay, regarding simulating software, I'm not aware of any. I haven't used any. But of course, here we have been addressing the problems theoretically. I mean, when you look at an algorithm theoretically, you can always give a mathematical proof as to its correctness and the time complexity. So, using the philosophy of the sequential algorithms, I mean, extending it, we have been proving the correctness of the algorithms and analyzing them mathematically. And on any real machine that is there, these algorithms would be simulatable. Because we have been focusing on models which are self-simulating. That is where a PRAM with a small number of processors can simulate a PRAM with a large number of processors. So even if you design an algorithm for a PRAM with a large number of processors, you can always scale it down when you have a PRAM with a small number of processors. So you could say that this body of knowledge runs a little ahead of the technology. The parallel architecture, which will actually exploit these algorithms, are yet to come. Both of them are good, but then they also have severe limitations. Yeah, as the other participant is suggesting, we can use MPI, GPU, etc. for converting them into code. Yes, MPI is available today. message passing interface, for example. But converting them into MPI code is somewhat cumbersome. It will be a little harder than writing a conventional C program. I haven't used CUDA, so I'm not familiar with it. There would be courses on parallel computing as opposed to this course, which is on parallel algorithms. Parallel algorithms has more of a theoretical flavor. This is somewhat futuristic. We are looking at the problems from the algorithmic perspective and trying to philosophically pose the question, which are the problems that are easily parallelizable? So eventually, when we have an efficient parallel architecture, we will know how the problems, which are the problems that are easily parallelizable. Like the notion of NP completeness in the domain of sequential computation. We know which are the problems that are efficiently solvable in polynomial time on single processor machines. Similarly, we are asking which are the problems that are efficiently solvable, that is solvable in polylogarithmic time using a polynomial number of processors. These algorithms have been designed on a theoretical model. So when you have a machine which mimics the power of the theoretical model, you can run these algorithms without any change. And we do have shared memory architectures today, but then the problem with these architectures is that the number of processors in them will be rather small because of the fan-in, fan-out constraints. So there are certain technological impediments to making, machines with large degree, shared memory machines with large degree of parallelism. But of course, in the second half of the course, we have been looking at interconnection network algorithms, and there are machines with a large number of interconnected processors. So those algorithms are, more readily amenable to practical use. But then the question is, when you look at a problem mathematically, you have to answer the question: how far is this parallelizable? Is this problem at all parallelizable? For example, some problems are solvable very easily in the sequential domain. For example, depth first search is a very easy problem from the sequential perspective. This is a linear time algorithm. But when you look at it from the parallel perspective, you find that it is a incomplete problem for MC reductions. Therefore, you do not expect this problem to be easily parallelizable. So that is a sort of investigation we are doing in this space. So of course, these algorithms are not dependent on architectural advancements. You can see that the model that we have assumed is a very rudimentary one. The only assumption is that there is a shared memory which is accessible by all the processors. So the immediate technical impediment is that it's not possible to design a machine with a very large number of processors because of fan-in, fan-out constraints. Well, the theoretical assumption that we have made is that any memory location is accessible by any processor in any clock cycle for read or write purposes. So this is a little unrealistic even for read purposes when the number of processors is large. For example, if the number of processors is beyond 100, then it's technically not very feasible today. So that exactly is the main theoretical assumption that seems to be impractical today. But then as an algorithm designer, you shouldn't worry too much about the practicality, because after all, you are posing the question, which are the easily solvable problems and which are the ones not. And once you make sure that your model is capable of simulating a model of the same kind with a large number of processors, then you can always scale down. So with that caveat, you go ahead and design algorithms assuming as many processors as you can. So that will explore them, that will let you explore the limits of parallelism. So that's exactly what we are trying to do here, explore the limits of parallelism. Okay. Okay, so I suppose that's the end of the session. Thank you very much.